some maybe new concepts or ones that you have already seen, at least the names of different types of materials, and then we'll talk about boundary conditions, which are important as we move from now on. And then we'll introduce also the conduction current that we talked a little bit before, but I want to make sure that we introduce it so we clarify a little bit what is the convention we are using about the direction of the current. And then we're going to go to introduce the concept of the capacitance. So just to say a few things, what we have seen in our work so far is that we have different charges with different distributions, and those generate different fields. And so how you solve the problem, how you find the total field depends on what you have seen before, but it's important to always synthesize the things that we have seen so we don't start from the beginning. And then so if your source is complex and you can make it up from different pieces, so then you can use superposition. In fact, you can use superposition for the fields, all right? So you can take each part of your source separately. You can, if you have the formula, you can use it, and then you can sum up all of the electric fields. That's what we found in the homework, all right, with a square. We also saw in the homework the spherical charts that we had seen before, but this time it was held by inside the dielectric material. So the sphere was dielectric, the charge was distributed uniformly like before. The only difference in this sphere was that the material inside the sphere had an epsilon, not epsilon naught. It was a dielectric material. It did not have, it was not free space. But the formulas in general remain the same, all right? What we're gonna do right now is to bring all of this together. And first of all, talk about the dielectric materials, because we are gonna see them a lot from now on. And then eventually we're gonna introduce also magnetic materials. But we'll start with the dielectric materials, which are important in electrostatics. Then from there, we're gonna talk about what happens at interfaces between dielectrics. Yes. Oh, okay. They don't. I'm sorry. I will need to put it up because I have it. Obviously, I picked the wrong file. Were they both for individual and team?
Team has like a whole bunch of math in it, but it's not relevant to the question.
Okay, let me, since you're asking, can I just go and check it, see what it is? Let me see. So let's do this. Make sure that I understand what the problem is. Okay, I may have picked the wrong files because the way it's asking you to. All right, so we're talking about a debate. You looked at the team 3 with solutions. Is that not the one?
So all this is like calculating fields at locations, but you never actually state like what do the work to find what location has maximum speed.
Sure.
But your answer is in terms of multiple, that's not the answer.
It's not an answer. I give you here. The location is shown. What did I say? C, B, I'm sorry. This is, okay, that was supposed to be total field at point D. Okay. electric field point B. That's what I meant to say, not D. I apologize for that. Yeah. So D is supposed to be B. We don't have D. So B point is here. You see the point B? No? You see point B, right? So the only mistake I've made, instead of B, I put D. I don't know what I was looking at, but is the maximum is at point. So I have calculated the maximum at point B. Well, no, C and B was supposed to be, all right? So the total field at C is this, the total field at B, I will correct that, is this. Because if you observe how the fields go when you superimpose, all right? The math, you wanna do it with math? You can do it with math. The only thing with math, I did it by practically observing how this goes fast, how fast down this goes, how fast down this goes, and how you sum it up. All right, what in fact happens at this point versus what happens at this point. So if you want to do it mathematically, I did not do it mathematically for one reason, because you cannot differentiate at these points here because they have a discontinuity. You cannot differentiate at a point where there is a discontinuity in field. So the only thing you can do, if you want, all right, is to sum this up here, sum this up here, and then if you want to differentiate, you have to do it from here to here. It's going to be something like this. It's going to be something like this. All right. The reason I did not do it this much is because if you want me, I can draw it for you, but I did not differentiate. Because you cannot differentiate in these points where it's the maximum. This is here the maximum.
The question asks for a location. It doesn't ask us to calculate field strengths.
The location, B. It's a location.
So if I just wrote B, would that just answer the question?
No, without calculating the field.
What if you calculate the field?
So how did you do it? I want to know. Maybe instead of getting the whole class in the discussion, why did you not come after the class and we can discuss it? All right, that's the best. I would like to see how you did it, and then we can discuss the in between. All right, so let me continue. Okay. All right, so we have a number of different dielectrics on the basis of how the dielectric itself changes. So, and there is one constant that we are using to characterize how the dielectric behaves. That is epsilon. Now, every material has two constants. Two constants, exactly. One is the dielectric constant or dielectric permittivity, and the other is the magnetic permeability, epsilon and mu. In dielectrics, always mu is mu zero, mu sub naught. And we have not seen it yet because we are in electrostatics. But as we go to magnetostatics, then you're going to see that, all right, involved in the equations. So now we are also now pay attention to epsilon. So a material is homogeneous if epsilon is a scalar and is epsilon sub r is constant everywhere. So D is going to be equal to epsilon E. All right. So D and E are related through that scalar. Isotropic is when epsilon is scalar again. It may not necessarily be constant everywhere, but it's a scalar, and the relationship between D and E is given here. So a scalar epsilon makes the material isotropic. A scalar and constant epsilon makes it also homogeneous. All right. So when you say homogeneous, you don't need to say isotropic. But if you say isotropic, it's not necessarily homogeneous. Linear is one where epsilon does not change with time. And there are cases in materials, and it depends also specifically on how you operate them and what kind of frequencies when you go to electromagnetics, where epsilon then changes with time. Epsilon, in other words, changes with frequency, and therefore it changes with time. All right. Those are called nonlinear if that happens. If epsilon does not change with time, it's called linear. So homogeneous if it's scalar and a constant, inhomogeneous if it's scalar but changes in space. All right. So that's the next. Isotropic if it's scalar but not necessarily a constant. Anisotropic when epsilon is a tensor. And for example, I give you an example. You remember tensors, they have different, it's like a next higher order above vector. So it's like a product of vectors, all right? But now you may not see the importance of this. If you go to a higher class in electromagnetics, you see why it is important to have that, because there are a number of materials that are anisotropic, which means that if I have an electromagnetic field, then along the x, E sub x is going to have a different epsilon multiplied with it to find D. And sometimes what also happens is that D, the relationship between D and E is not anymore a scalar relationship, like multiplied by a constant, a scalar product, but is a tensor product. So epsilon affects D not only in magnitude, but in direction. All right, so that's what it means. That's an anisotropic. What it means really is the waves behave totally differently as you go along the different directions in the material. That's because of the structure of the material. And then nonlinear, where you have a material whose properties change with time. All right. Now for us in this class, everything is going to be on the left. So homogeneous, isotropic, and linear. We'll have all of these. Yes. Yes, exactly. And then the structure, exactly, the arrangement of atoms. Right. Okay. Now we spoke about conduction current. In fact, we talked very briefly about it, but we spoke a lot about how electrons move inside the material. All right. And also we said that if we have a perfect conductor, so sigma goes to infinity, electrons move freely. Here, of course, if it's perfect conductor, also we said, I don't want to miss that inside the perfect conductor, how much is the field? 0. All right, there is no, in a perfect conductor, there is no field inside, 0. However, a resistor, for example, is not a perfect conductor, but is made out of a conducting material. It's like a piece of material, like a rod, all right? And it's designed with a specific conductivity. So there is a current that goes through, but it's not an infinite conductor. Now, the material that has been utilized has a particular sigma. And what that says is that when here we excite a field, or in other words, we connect this material with the battery that has a plus on the left side and negative on the right side, that excites an electric field E, which then goes from the plus side, the electric field, will apply along this. All right. Now, the electrons are negative charges. So if the electric field applies like that, the electron fields will go like this, all right? Because usually the field lines go towards the electron. So they will move in that direction, all right? However, even if the electrons move like that, they create a movement, like they create the impression that the holes that they leave behind move into the other direction. By convention, we consider as the conduction current the movement of holes, even if the electrons are moving. But it's a convention, all right? So always we show the conduction current to have the same direction with the electric field. And the density, what happens, for example, if you have a material like a road, and then it has an area, the current is going to distribute around that. So we don't have a total current, we just have a density, and then you have to integrate the density over the area, the cross-section of the material, like here, to be able to find the total current. The current density is equal to sigma E, and that is called the conduction current density, all right? And if you want to find the total current that flows through this conducting material, you have to integrate, find the cross-section of the conductor, and then integrate along that cross-section the current density, all right? And then you find the total current. So that is so we remember about the convention we have introduced for the conducting current. Okay, boundary conditions. When we have dielectrics and then we have air, and we may have multiple dielectrics, then the question is what happens at the interface between the materials, all right? How does the field change? And as a matter of fact, the problem that we solved showed indirectly what happens. You're gonna see it through the two conditions. So let's consider that case. We have a planar dielectric that has epsilon here and nu. And then we have a electric field in region 1. Let's call that 1 here. And then we call that 2. And because we have the way I select, and we normally select a Cartesian coordinate system for the planar surface, we select it so X and Y, for example, are on the surface of the interface, and Z is perpendicular, all right? So in that case, yes, generally we have 3 components in the electric field, but here we indicate them as the perpendicular with this, like we showed perpendicular, we showed like that, all right? And the parallel components, we show them like this. If we introduce that kind of symbolism in that for the perpendicular and the parallel, then instead of 3 separate components, we're talking about 2. Perpendicular is the Z, and the parallel components will be either X or Y or both, all right? So what does, in fact, here, the 2, and I will go back, the 2 conditions that apply on a air dielectric planar interface. In fact, even you will see here is planar, you will see that apply on any other interface, all right? But let's consider the planar for now, is that the perpendicular component of the flux density is continuous here, but the parallel components of the electric field is continuous, okay? Now, what does that mean? If the perpendicular components of the electric flux density are continuous, what will happen to the perpendicular components of the electric field? Are they going to be continuous or they're going to be something different? If the perpendicular components of D are continuous, all right, this is D1, and let's take the perpendicular here, and then this is D2. How much is D1? D1 perpendicular is gonna be epsilon naught in free space, E1 perpendicular. Let me just change it because I used the other one. So 1 perpendicular, D1 perpendicular is epsilon naught E1 perpendicular. And D2 perpendicular is epsilon E2 perpendicular. So since the D's are equal at the interface, and because they have different epsilon, the two media, it implies that the electric field, the perpendicular electric field, is going to be discontinuous on this air dielectric interface, okay? Now, contrary to that, the parallel components of the electric field are equal. And again, because of the relationship between the electric field and D, that implies that the parallel components of the D vector, which is the electric flux density, will be discontinuous, all right? So the most important thing is to remember these two formulas, which only talk about what is continuous, all right? So continuous perpendicular or component to the interface of D, and continuous are the parallel of E. All right, these are the boundary conditions on an air dielectric interface. Now, why? Here is an explanation, because somebody asked me why they are discontinuous. And the reason that is, you can prove those formulas. We did not want to do it here. The proofs tend to be not difficult, but take time. And I think you will see those proofs later if you decide to do more in this area. But very simply to explain it, why is it like that there is discontinuity? Okay, in the normal. If I, for a moment, in continuity in the normal, excuse me, in the D, and discontinuity in the E. According to Gauss's law, all right, if we had a charge, if we had one charge or a number of charges on the interface, at those points where we had charges, then the divergence of D would be equal to that charge density. All right, that's Gauss's law. We have seen it before, we have used it. Now, in this particular case, there is no Q, there is no charge. I did not mention, if I tell you you have an air dielectric interface and I do not tell you anything about charges, there are no charges, all right, on the interface. Okay, if there were any, I will tell you. So at this moment, let's assume that since we don't have charges, I raise that and that becomes 0. And now let us assume that I have an infinite interface and I have this problem where I have one-dimensional and one-dimensional field, which means that E will be along the Z direction, all right, 1D, and D, which is the flux density, will be along the Z direction, which implies that the Gauss's law here is going to translate into this one, that this here is 0 since we don't have charges, all right? So as you go through the interface without charges, the derivative of D with respect to Z, it will have to be 0, all right? Which also says that if I, instead of having derivatives, I go to differentials. So that means that if I take a point just above the interface, say, and a point just below the interface, P, then the difference in the values of D and A and B divided by this tiny distance that separates them, it should be either Q if there were a Q there, or it should be 0. In our case, there is no Q, therefore, it's 0. And because it's 0, then these two vertical components are equal. Because they're equal through the interface, the electric fields are different. So because what is D sub A? D sub A is epsilon naught EA, and those are the vertical components, all right? Which is epsilon EB, which means that EA will be epsilon over epsilon naught EB, and because epsilon, okay, and because epsilon is epsilon R epsilon naught divided by epsilon naught EB, it means that finally we have that EA will be epsilon sub R EB. And that's what happens in this particular case where we have a simplified case, all right, of one-dimensional field. Okay, so these are the two important boundary conditions for an air dielectric interface. And with that, we'll stop with this. It's important material to incorporate. It's only the dielectric boundary, or is our only boundary conditions on a planar dielectric air interface. As we move now to other materials, then we'll see additional boundary conditions. I do not want to list them all here and then use them later, all right? We're going to introduce more as we use them, so you remember them also. Any questions that you have in regards to this? All right, then what I would like to do is to introduce capacitance, which you have seen. You have seen capacitance, but you have seen it in circuit form, is that right? And maybe you have seen it in physics too some time ago. So here we are gonna introduce the concept of capacitance from the electric fields point of view. And then we're gonna show how that becomes the capacitance that you have seen in circuits. But then if we introduce capacitance from the electric fields point of view, then we are gonna have the capability to compute the capacitance of fairly complicated capacitive structures, all right? Because I think what you have seen are probably the simplest one, which is the parallel plate with one material. All right, so here is what I would like to do, first of all. What I would like to do is to take this complex geometry. I will take this part and I will copy it, and then I will remove it. Copy, and then rather, I should have said cut. Remove it, cut. Okay, do you remember the problem we solved of a planar charge distributed on an infinite perfect conductor? Do you remember what happened when we solved this problem? What did we find that is happening to the electric field? Do you remember how it changes? Constant. Now, that is true, and it's constant everywhere on the surface. Okay, now also constant is the value, right? You say it's some kind of constant value, but let's talk about the direction of the field here. also. What kind of direction this electric field will have? Towards will point towards the negative charges, all right? Because it goes away from the positive charges and it goes towards the negative charges, all right? This is fundamental. So, okay, having said that, let's show how this is gonna go. Okay, and that's gonna be constant. It's gonna be, and we found, as a matter of fact, that this field here, E, which is along the perpendicular direction, along the Z. Let's assume that this is Z direction. In fact, the opposite. For a second, let's assume this is the Z direction. Then this one, E sub Z, that because it bothers me. E sub Z is, we found at the time, that was the charge Q sub S divided by 2 epsilon naught. That's what we had found at that time, okay? And that is the Z direction. Now, what is gonna happen if we take this field and then we keep it the way it is, and then we bring another conductor that has charges, but the charges are the same, identical, but positive. What do you think is gonna happen? What is gonna happen is what I had before. Let me erase this, okay, and say paste, and put it here. And as a matter of fact, so move that a little further down, okay? So let's call that, to just call this EZ2. We have seen it before, all right. And it goes down. What happens with that now? We have the same, we have an infinite conductor, same charge, but positive. All right, same charge distribution, but it's positive, which means that the field is gonna be identical to the one we had before, but with the direction that goes away from the charge, the red. But these two, EZ1 and EZ2, have now, they're identical, both in direction and in value. So then if we have the two together, we use superposition, all right? And in this case, we had, since it's dielectric in there, so we have superposition, we apply superposition, and the sum of the two will give us exactly what I have in here. All right, this is the total field along the Z direction inside this geometry, the two conductors, which eventually we're gonna call the capacitor. Now, what I do here is the following. How do I create those fields? How did I create those fields? I put a battery, and the battery connected, as you see here. The positive pole of the battery connected to the upper, so that's why the positive charge flew from the battery to the surface. And then the negative pole of the battery was connected to the lower, and that's how the negative charges went there. Okay. Now, using the formula that connects the potential to the electric field, what we have here, remember we have, since the electric field goes from 1 to 2, we had found, as a matter of fact, that the relationship between the electric field and V, the potential, that, so I can write it here, we had found that E was minus gradient of V. V is the potential there, all right? Because of that relationship, then we transformed, we took the integral from 1 to 2, which means that instead of having potential, I took the difference between the two values of the potential, all right? Between 1 and 2, which gives us voltage, all right? The integral of the potential between 2 points gives us voltage. The integral of the gradient, rather, of the potential between 2 points gives us voltage. It's like one potential minus the other. If therefore apply this, and from 1 to 2, that gives me the voltage I apply, which is V sub D, and that's the negative from 1 to 2 of V dot dz, which in fact gives us that V sub D is equal to the surface charge multiplied by the separation between the two conducting plates and divided by the dielectric constant, all right? So what is the total charge on each one of these planes? Since it's uniformly distributed, as we assumed, is the area of each plane, all right, multiplied by the charge density. And that gives us the total charge. Positive on the upper plane, negative on the lower. So now then, I can take this expression for V of D, which is the potential between the two grounds, the two conductors, and then I can write it in this form, where A times B is the area of each conductor. And therefore, we write this expression for the voltage, which you have seen for a parallel plate capacitor from physics. And then we now introduce the concept of capacitance, all right? As Q as the ratio of the total charge is divided by the voltage that applies across these charges. And that gives us the capacitance, which is in this form. And this is the expression of the capacitance of a parallel plate capacitor. This is called what we just saw, the parallel plate capacitor. All right, now we have some time then to see now why this is important. You may have asked yourselves, you remember from circuits what happens when you have two capacitors in series? What happens? Yes. And then if they are in parallel, you just sum them up, all right? Where do these things come from? Do you know? How did we make the decision that this is true, which we have done?
Parallel one, it's kind of like the plates are merging together.
So we're going to find it if you go and explain your capacitance in the form of fields and voltages, then you can find all of these formulas. All right. So here, let's assume, I'll give you some examples. Let's assume that we have here a parallel plate capacitor. All right. And duplicate that. Which also has A and B in dimensions, all right? And I will do it on both of them, okay, here. So this is A, B, and this is the distance between the two. Let's say call it H. But now, what are we gonna do is, we are gonna assume that this capacitor who is fed by a similar battery has two separate materials. So one is, let me see, yes, that's good. One is like this. All right, and the other It's like this. So one is gonna have this one, this shape, and it's gonna have a different dielectric constant. And the other is gonna have, so one is gonna have here epsilon 1, epsilon 1, which is epsilon sub r 1, epsilon naught. And the other underneath it, no, this one, is gonna have a different dielectric constant. And let's try to find now the capacitance for this one. What is gonna happen to the electric field? Because here you have the same kind as before. Here we have all of the positive charges. And then here down there, we have all of the negative charges. Negative. Okay, how will the fields go? How the field, now we have two materials, and therefore we're gonna have one field in the green one field in the red one. Say the field, the charges are uniformly distributed on both plates. So how will the electric field lines go? From top to bottom, all right? So the electric field lines or the flux density, because it's the same, will go like that. All right, as we saw before. Okay? But we don't know how much it is because we don't have the same geometry like before. The only thing we know is the following. That if I were to put this one as one material, I will put it here just to be able to show. Let's look at that cross section. All right, the top one is the green. So let me say this is where the currents are, the charges are. So positive here, negative down there. That's negative down here. I use that. Okay, the electric field goes like that. The flux densities go like this. All right, so this is D1, this is D2, and they're along the Z direction. All right, so D1Z, D2Z. Okay, we don't have any other field components. What do we know from the boundary conditions that we just talked about? What happens at the interface? These two are continuous, okay? So the D's through the perpendicular components at the interface are continuous for D. So if this, for example, is H, and this is H1, H2 will be H minus H1, all right? Let's call that H2. All right, now we connect that way voltage source. Now let's try to find, and also what we know is that D1Z equals to epsilon 1 E1Z and D2Z equals to epsilon 2 E2Z, all right? And these two are equal, which means that E1Z equals epsilon 2 over epsilon 1 E2Z. All right, what else do we have? we have that the integral from 1 to 2, the integral from 1 to 2 of V, excuse me, of E dot dz will be equal to VD, which means that E, since E is constant with the exception of, it's a constant everywhere with the exception of the interface where they jump, all right? So E1Z H1 plus E2Z H2 is equal to VD. That's what we found from there. And I will rewrite it, 1Z H1 plus E2Z H minus H1 equals V sub D. How much is E1Z? Is epsilon 2, epsilon 1, E2Z H1 plus H minus H1 E2Z equals VD. And then from here, we have that E2Z equals VD. And then underneath it, we have H1, E2 over E1, plus H minus H1. Okay, so we have this. Now, why is that important? Why is E2Z important? Because in this particular case, what do we know? We know that D, from this, the divergence of D at any point on the conductor now is equal to QS. And therefore, from there I have, because D is 0 inside the conductor, but not 0 outside, practically I will have that D right here underneath in this conductor or in this one, D1Z, therefore, just on the upper conductor is equal to QS, all right? Which tells me that E1Z is equal to QS at that point over epsilon 1, and then E2Z equals to QS over epsilon 2, see, for the same reasons. And therefore, I can go in there and find a relationship that gives me Q sub S, because I did not give you Q sub S, I only gave you the voltage, all right? That's the only thing. Therefore, I can go in this relationship here, which in fact, we're gonna do it more in detail next time. I just wanna introduce you. You're gonna find Q sub S, and then from here, we are gonna find Q sub S, and from Q sub S, we're gonna find Q. And from Q over V sub D, we will find the total capacitance, which in fact, if you assume that the one dielectric was one capacitor and the other dielectric was another capacitor, that practically you will find that 1 over C sub T is equal to 1 over C1 plus 1 over C2. We will see that in detail. So practically you can prove now using the electric fields that if you put 2 capacitors like this, it's like you have a series, all right? And we're gonna also show the parallel next time, and then you can have other combinations. But this is only on the basis of the electric field. So with that, I will stop today and I will give you an exercise, which is on, let me go here. exercise. Okay, it's exercise 9 for you. Okay, and it's a relationship between a capacitor and the voltage. You will see it for Wednesday. All right. Wednesday. Ah.
So for what for if the electric field is proportional to